For years, if you followed climate science even casually, you learned a fairly simple story about the two poles. The Arctic was in serious, fast-moving trouble, and the Antarctic was the confusing exception, holding relatively steady, sometimes even gaining a little sea ice while everyone worried about the North. That story just fell apart on both ends. A study published just last week found that a slowdown scientists had been quietly hoping was real progress in the Arctic wasn't real at all, and thousands of miles away, in the Antarctic, a ship full of scientists got stuck sheltering from a storm this past February and stumbled onto something that simply shouldn't have been visible, an island nobody had ever properly charted, sitting right where retreating sea ice used to hide it. Two different poles, two different research teams, and both walked away from this year with the same basic reaction. This isn't what we expected. Let's get into both stories, because understanding them together tells you something neither one tells you on its own. Let's start in the Arctic, because the story there is genuinely a reversal, not just a continuation of bad news. Back in the early 2020s, researchers tracking Arctic winter sea ice, the maximum extent the ice reaches each year, typically in March, after growing all fall and winter, noticed something that looked cautiously like good news. The pace of winter sea ice loss appeared to weaken. After decades of decline, the trend seemed to be flattening out, and some scientists wondered whether the Arctic's winter ice cover might be stabilizing, even as the more famous summer melt continued to worsen. That's not an unreasonable thing to hope for, and it's exactly the kind of finding careful scientists are supposed to sit with, rather than either dismiss or celebrate too quickly. A new study published in the Proceedings of the National Academy of Sciences, led by Duo Chan at the University of Southampton, just added 2 more years of data to that picture for winter 2025 and winter 2026, and the results undid that hopeful red. Both years came in at or extremely close to the lowest winter sea ice, extents ever recorded since satellite monitoring of the Arctic began back in 1979. In fact, separate tracking from NASA and the National Snow and Ice Data Center found that this year's winter maximum, reached on March 15th at about 552 million square miles, was so close to last year's peak that the 2 years are considered statistically tied for the lowest on record. When Sean's team compared this new data against climate model simulations from the Coupled Model Intercomparison Project, the same modeling framework underlying the IPCC's most recent major climate assessment, the 20-year trend in Arctic winter sea ice showed a statistically significant decline, not a plateau. In the researchers' own words, this sharp drop changes the way scientists interpret recent Arctic winter sea ice change. What looked like a pause in the early 2020s now appears to have been a temporary slowdown, not a stabilization, and the long-term downward trend picked right back up. I want to explain why winter sea ice extent actually matters, because a lot of public attention understandably goes to the dramatic summer melt season instead. Think of winter maximum extent as the starting inventory the Arctic has to work with each year before the summer melt season begins stripping it away. A lower winter peak means there's simply less ice available heading into summer, which means the following melt season has less of a buffer before it starts cutting into ice that's been there for multiple years, rather than ice that just formed a few months earlier. Multi-year ice is thicker and more resistant to melting away completely, so a shrinking winter peak, sustained over years, gradually erodes that buffer and leaves the whole system more fragile going forward, even in years when the summer melt itself doesn't look unusually dramatic. There's also a very specific current mechanism behind exactly where this year's Arctic ice loss is concentrated. And it's worth understanding because sea ice loss is rarely uniform across the whole Arctic Ocean at once. As of early July this year, overall Arctic sea ice extent was running at the 4th or 5th lowest level on record for this point in the season, a little over 9 million square kilometers, roughly 1.5 million square kilometers below the 1981 to 2010 average. But that shortfall isn't spread evenly. It's concentrated almost entirely along the Atlantic side of the Arctic, the seas near Scandinavia and the edge facing the North Atlantic, while ice conditions across the rest of the Arctic Ocean are running closer to normal. June this year was an unusually stormy month over the Arctic Ocean, when persistent winds blowing up from the south specifically funneled warm air into that Atlantic sector, while other parts of the Arctic actually stayed on the cooler side. Scientists sometimes describe this pattern as the Atlantification of parts of the Arctic, warmer Atlantic water and air increasingly pushing into a region that used to be reliably cold year-round. I'm essentially importing a warmer ocean regime into what used to be classic polar territory. That process isn't just about warm air sitting on top of the ocean either. In a normal, more insulated Arctic, a layer of colder, less salty water sits near the surface and acts almost like a lid, keeping a deeper layer of warmer, saltier Atlantic origin water from mixing upward and reaching the ice from below. Researchers studying the Atlantic gateway into the Arctic, particularly around the Barents Sea, have been tracking that surface lid gradually weakening in some areas, which lets warmth from below reach the underside of the ice more easily, on top of whatever warm air is arriving from the south. When both of those things happen in the same place at once, that region can lose its ice cover much faster than a spot experiencing only one of those two effects. That's exactly the kind of mechanism-specific detail that a simple headline number like sea ice is at record lows doesn't capture on its own. It's also worth noting that the Antarctic's own winter side of the calendar has been showing the same kind of strain as its more widely reported summer minimum. Separate NASA tracking found that Antarctic sea ice reached its own annual maximum extent back on September 19th of last year, and that maximum came in as the second lowest ever recorded by satellite, trailing only the record winter low set in 2023. So this isn't only a story about how little ice is left standing at the end of an Antarctic summer. The continent has also been struggling to build back a normal amount of ice during its own cold season, in the same general stretch of years when that hidden island first became visible. Now let's go to the other end of the planet, because the Antarctic story this year is, if anything, even stranger, and it comes with a genuinely remarkable discovery attached to it. For most of the satellite record going back to 1979, Antarctic sea ice behaved almost like the Arctic's opposite. While Arctic ice declined fairly steadily decade after decade, Antarctic sea ice actually held roughly steady, and by some measures even trended slightly upward through the 2000s and into the mid-2010s. Scientists had reasonable, if incomplete, explanations for that difference, tied to things like the shape of the Southern Ocean, the behavior of winds circling the continent, and deep geological history. A separate, unrelated study on Antarctic ice sheet formation even found that Antarctica became covered in land ice tens of millions of years before the Arctic did, because slow-moving waves deep in the Earth's mantle actually pushed up a huge stretch of East Antarctica, including the Gamburtsev Mountains, to an elevation high enough for glaciers to take hold well before falling carbon dioxide levels alone would have made that happen. That's a genuinely fascinating piece of deep-time science, and the researchers behind it made a point of noting that if shrinking CO2 levels were the only factor at play, you'd expect both poles to have iced over in a more symmetric, matched way. Instead, Antarctica got a geological head start that has nothing to do with the modern climate story at all. That deep history is part of why, for a long time, a comparatively stable or even growing Antarctic sea ice cover didn't seem all that suspicious. Then, right around 2016 and 2017, something changed abruptly. Antarctic summer sea ice extent began dropping sharply, and it hasn't really recovered since. According to the National Snow and Ice Data Center, this is now the fourth consecutive year that the Antarctic's summer minimum extent has fallen below 2 million square kilometers, a threshold the continent had essentially never crossed before this recent stretch began. This year's summer minimum, reached in late February at just under 1 million square miles, was actually a bit higher than the unusually low levels of the 4 years right before it, which is a small silver lining, but it still came in well below the longer-term average, and nowhere close to erasing the broader shift that started back in 2016 and 2017. Here's where the story gets genuinely remarkable. Back in February of this year, an international team of 93 scientists and crew members set sail aboard the German research icebreaker Polarstern, operated by the Alfred Wegener Institute, to study ocean currents, sea ice, and the flow of cold water out of the Larsen Ice Shelf in the northwestern Weddell Sea, one area that plays a genuinely important role in how the whole Southern Ocean circulates. Rough weather forced the ship to seek shelter near Joinville Island, close to the tip of the Antarctic Peninsula, and while they were sheltering, the crew noticed something odd sitting a short distance away that, from far off, looked almost like a dirty iceberg. It turned out to be an entirely uncharted island. The location had only ever appeared on nautical charts as a vague, unexplained danger zone flex, because for as long as anyone had been mapping this stretch of coastline, thick sea ice had simply obscured whatever was actually underneath it. Retreating ice had finally exposed solid ground that had been sitting there the whole time, hidden in plain sight in one of the more heavily studied corners of Antarctica. While they were in the area, the team also took direct measurements of the surrounding sea ice, and what they found illustrates just how uneven and dramatic the changes there have become. In some shallow areas closer to the coast, tidal action and general movement had pushed ice up to as much as 4 meters thick. Just a bit farther out, the ice thinned dramatically to around 1.5 meters and was far less deformed and jumbled than the thicker coastal ice. The researchers also documented strong surface melting across the region, with snow cover disappearing entirely in places, and the exposed ice underneath taking on a distinctive bluish or grayish tint rather than the usual bright white. Beneath the surface, they detected distinct layers of fresh meltwater sitting on top of the denser, saltier ocean water below. And that layer of fresh water doesn't just affect how quickly the ice above it melts, it also affects the tiny algae and other microorganisms that live in and directly beneath the ice. Right? Organisms that play a real measurable role in how the Southern Ocean absorbs and cycles carbon. This wasn't a research team looking for evidence of dramatic change and finding what they were looking for. This was a routine current and ice flow survey that got redirected by a storm and stumbled into physical proof of just how much this specific stretch of Antarctica has transformed since Antarctic sea ice was still considered the stable, boring half of the planet's polar story. The current, present moment Antarctic picture backs all of this up. As of early July this year, overall Antarctic sea ice extent was sitting at the 6th lowest level on record for this point in the Southern Hemisphere's winter growth season. June saw unusually low atmospheric pressure spread across almost the entire Southern Ocean, especially concentrated in the Amundsen Sea, and that low pressure pattern is very likely part of what's been driving warmer than normals. Conditions and suppressed ice growth specifically near the Antarctic Peninsula, right in the same general region where that hidden island turned up. It's worth being precise about what connected actually means here, because the Arctic and Antarctic are not the same physical system reacting to each other directly. They're separated by an entire planet, and a low-pressure system over the Amundsen Sea doesn't reach up and cause a storm over the Barents Sea. What connects them is the shared, planet-wide warming trend driving both regions, not some direct mechanical link between one pole and the other. That distinction matters, because it's exactly why researchers pay close attention to moments when both poles move in the same direction at once. It's a genuine test of whether what we're seeing is two unrelated regional stories that happen to coincide, or the signature of one coordinated, whole-planet response to a shared cause. This year, for both the freshly reanalyzed Arctic data and the freshly exposed Antarctic coastline, that test came back pointing toward the same answer. So here's the part that ties both of these stories together and explains why researchers are genuinely recalibrating how they think about the planet's ice right now, rather than just filing each pole under its own separate expected narrative. For decades, the Arctic is collapsing while the Antarctic mostly holds steady was a defensible summary of what satellites were actually showing, and it had real physical explanations behind it, tied to genuine differences in geography, ocean circulation, and deep geological history between the two poles. What's caught scientists off guard this year is that both of those separate stories just moved in the same direction, hard, at the same time. The Arctic's brief winter pause, which some had cautiously hoped was a sign of stabilization, turned out to be a temporary lull before the decline reaccelerated to record lows. And the Antarctic, long treated as the exception that proved the rule wasn't universal, has now spent nearly a decade behaving less and less like an exception, with a sharp, sustained shift beginning in 2016 and 2017 that shows no real sign of reversing, punctuated this year by literal new land being exposed for the first time in living memory. This isn't the first time both poles have shown simultaneous stress either. During the same week last summer, daily sea ice extent in both the Arctic and Antarctic simultaneously ranked third lowest in the entire 47-year satellite record, a genuinely unusual coincidence that researchers noted at the time. What's different now is that the Arctic side of that coincidence just got a fresh, statistically rigorous confirmation that it isn't a fluke, and the Antarctic side just produced a vivid, almost unbelievable physical illustration of the same underlying trend. I want to clear up a common misunderstanding here, because it's an easy one to make and it actually matters for getting this story right. Melting sea ice, on its own, doesn't meaningfully raise ocean levels because sea ice is already floating and already displacing its own weight in water. The same basic reason a melting ice cube doesn't make a full glass of water overflow. So the direct danger from sea ice loss isn't sea level rise. The real significance is something else entirely, and it comes in a few different forms. First, sea ice reflects a huge amount of incoming sunlight straight back out to space, while open, dark ocean water absorbs that same sunlight as heat instead. Less ice means more absorbed heat, which drives more melting, which exposes more dark ocean. I get a feedback loop that reinforces itself over time. That loop is a big part of why the Arctic has been warming roughly 4 times faster than the global average over recent decades. Second, sea ice acts as an insulating lid between the ocean and the atmosphere above it, and losing that lid changes how heat and moisture move between the two, which can influence weather patterns well beyond the polar regions themselves, an area researchers are still actively studying rather than fully settled on. Third, and maybe most tangibly, sea ice is a genuine habitat, home to everything from ice algae to seals to the animals that feed on them, and losing it removes that habitat outright, not gradually. Where sea ice loss does connect to actual sea level rise is indirectly. The same broad warming pattern responsible for retreating sea ice is also the pattern driving accelerated melting of land-based ice in Greenland and parts of Antarctica, and land ice sliding into the ocean absolutely does raise sea levels, because that ice isn't already floating and displacing its own weight the way sea ice is. It's also worth mentioning that studying any of this, especially the living ecosystem living in and under polar ice, still genuinely requires people, not just satellites and robots. Scientific diving programs, training researchers to work directly beneath Arctic and Antarctic ice have been expanding in recent years. And one British Antarctic Survey marine biologist involved in that kind of fieldwork put it simply: dragging a net across the seafloor to sample it would destroy the very habitat you're trying to study. And a remotely operated submersible usually can only grab one specimen at a time, while a trained diver can collect a dozen or more organisms by hand without disturbing the surrounding ecosystem. That's a small but telling detail about how this research actually gets done. A lot of what we know about how fast these ecosystems are changing comes from people physically diving into some of the coldest, most remote water on the planet to check. I also want to be careful not to overstate what any single data point proves here, because that kind of restraint is exactly what the scientists themselves are practicing. One of the NSIDC researchers tracking Arctic winter ice put it plainly: a low year or two doesn't necessarily mean much entirely on its own. It's only when you view individual low years within the broader multi-decade trend that they start to tell you something meaningful about the overall trajectory of change. That's exactly the right way to think about everything I've just walked you through. Not as a single alarming headline, but as one more data point. In the Arctic's case, a very rigorously analyzed one, and in the Antarctic's case, a genuinely vivid physical one, both pointing in the same direction as the longer trend that's been building for years. So what happens next, and what's actually worth watching? On the Arctic side, September is when the Arctic reaches its annual summer minimum extent, and that number remains genuinely hard to predict this far out, since it depends heavily on the specific weather conditions over the following couple of months, rather than anything locked in by early summer. Current projections put this year's minimum somewhere in the range that's become typical since 2007, which is still well below the longer-term historical average, even if it doesn't set an outright record. On the Antarctic side, the southern hemisphere is still in the middle of its winter ice growth season, which typically doesn't peak until around September, so there's real uncertainty about how much additional ice the continent will manage to regrow before that low-pressure pattern over the Southern Ocean potentially eases up. Researchers monitoring both poles are also in the middle of a genuine technical transition right now, shifting away from an aging satellite sensor system that's been supplying sea ice data for years and moving toward a newer Japanese satellite instrument as the primary data source going forward, which is itself a reminder that this kind of long-term monitoring takes constant active maintenance, not just a single instrument left running indefinitely. I'll leave you with this. Neither of these stories is really about a single dramatic event. They're about two different research efforts, thousands of miles apart, both arriving at the same uncomfortable update to what scientists thought they understood. The Arctic's brief moment of apparent stabilization wasn't real, and new data confirms the long-term decline never actually paused. The Antarctic's long-standing reputation as the more stable. Resistant half of the planet's ice story has been fraying for almost a decade now, to the point where scientists are literally discovering new islands that ice used to hide. Two ends of the planet, two separate lines of evidence, converging on the same basic conclusion. I'll keep following both stories as the Arctic heads toward its September minimum and the Antarctic works through the rest of its winter growth season, and I'll bring you an update if either one breaks meaningfully from what the researchers are currently expecting. Stay curious, follow the actual published research rather than the headlines about it when you can, and I'll see you in the next one.